until we, yes, okay, woohoo, technology triumph. All right, so with that, welcome Jim Bednar. Jim has been a member of Pangeo since the very beginning and has attended almost all of these, almost the beginning. Okay. And he's here to tell us about, I think, a little bit of an expansion about what we talk about when we talk about the Pangeo stack. So yeah, take it away, Jim.
That's right. Thank you, Rich. There was actually a period where I was on the sidelines watching jealously what was going on in Pangeo and thinking, hey, that's a lot of cool stuff. And we've got a lot of cool stuff. It'd be great if they could be married together. And then we did marry them together and then did start using the tools that we were developing independently. A lot of them did start becoming used in Pangeo. And the whole experience with Pangeo is what's inspired this talk. And just for a little context, I work at Anaconda. Anaconda is not in the climate science field. We do a lot of projects with people who are in climate science, but we develop software for every possible scientific field. And so we've always had a little tension between being domain general and being domain specific. The more specific you are, the more directly a piece of software can solve a problem in that domain. But then the smaller the audience for that software, and then there are other tasks the software could do that are in different domains. And if you've made it specific to that domain, you have to write the software again. And one of the things I want to do here is just kind of look at Pangeo from an Anaconda perspective of not being tied to any particular field. And what does that mean? What does that, how does that end up? And is there a reason to do that? And I believe there is, and what I want to argue in this talk is that the core packages that are being used in Pangeo form a basis for doing science of any type. And in order to make that, and that's a lot of packages to list, so discussed with a lot of colleagues, we decided this has to have a name. And we're going to call this set of packages that are domain independent, the name that you see on the slides, SOSA. I tried to come up with something that didn't have so many words in it, and I failed. At least this one's pronounceable, but it was important. Basically, we need to say how this set of tools differs from any other set of tools. The Python ecosystem is full of tons of tools, and understanding how they relate to each other, which one to use in different scenarios, boiled it down to, well, this set of tools that we're going to talk about today is scalable. That means it can work on your laptop, it can work on a cluster, it can work on a supercomputer, it can work as big as you possibly want it to work, or as small as you want it to work. And that is not true of very many tools, so that word had to be in there. And then open source, there's a lot of talk of the modern data stack. Much of that is not open source. And so a lot of those are that's basically what powers today's enterprises, all of it built on open source, but usually with some heavy non-open source components, whereas this stack is only open source. So that had to be there. And then what is it a stack for? It's for analysis, it's for science, it's for engineering. And as soon as I put in science, I had people complain that, hey, I'm not doing science, but I want to use this. So as I put in engineering, I said, I'm not an engineer, but I want to use this. Analysis seemed to offend the least number of people. So there we go. And stack. I'm going to argue that this set of tools is a stack, in that a stack being a set of tools that you stack up literally to solve a problem. It's not an ecosystem. It's not, well, it's also an ecosystem, but more specifically, it is a stack. You put together a stack of tools to solve a particular problem. That's basically how things work in Python. So as far as my own background, I've been involved in some of these projects since long before I joined Anaconda, which is in 2015. I was a professor in neuroscience. Some of these tools were built for neuroscience. And then when I arrived at Anaconda, hired some of my old PhD students, and we stripped out anything that was related to neuroscience, which was almost nothing, because we always designed it to be domain independent, and then have applied it to many different domains since then. So that kind of leads into some of these tools. So to actually begin the talk, this is talk to Pangeo, because I want you guys know the most about the stack of anybody, and so I want feedback from you guys. But I also want every person on this call is almost certainly squarely in Pangeo for some of the things they do, and also doing some things that are really not exactly in the mainstream of Pangeo. Pangeo is a kind of loose thing, but almost certainly you have some parts of your workflows, some parts of your interests that aren't just entirely exactly covered by Pangeo. And I want you to think about those things and how the Pangeo stack might apply to those things, as well as what we normally consider Pangeo, which is quite climate science focused, or at least earth science focused. So if you think about the history of computing software in the scientific and engineering fields, it is just littered with projects that are in domain specific, for storing data, for reading it, for processing it, many times even for plotting it. Domain specific libraries for plotting, which offends me greatly, but there are a lot of those. There have been a lot in the past for how you analyze the data, how you model it, how you explore it. These have been developed for decades, and they're largely proceeding independently in the different domains, and each one of them has some great points and has some flaws. But typically, I would say the more established stacks are not cloud friendly. Pangeo, in fact, is a bunch of tools that were kind of reacting against things that were not ready for cloud, saying, hey, well, we're going to do the things that are ready for cloud. And a lot of those tools were tied to a specific desktop GUI, like a Windows system or maybe a Mac, or only ran on a certain OS. That really limits the size of your collaborators and people who can reuse your software. And many of them are not scalable. Many of them were written in a different era of Moore's law, where it was just the processor that was getting faster. And at that time, you were either on a supercomputer or you were on a single system, and it was either way. You were either only tied to a supercomputer or only on a single system. My own upbringing was all on supercomputer. But in any case, they were the tools were tied one way or another. And they were very domain specific generally, because the people who were developing them were developing to scratch their own itch or to solve their own problems. And that is great, but it's really a dead end. So given that every one of these tasks involves data, I'm going to argue that there's a better way, and it's pioneered by Pangeo. It came up with this name for it. And we're saying, hey, all that great code, try to set it aside, try to use the tools from Pangeo that are domain independent, and then selectively pull in the things that you need from the old stack. Focus on these tools and bring in anything else only when you need to. And so what's included in this stack? Well, it's tools that, in my opinion, since I'm giving the talk, I got to make this list. So I made a list of what I'm looking for in tools, and I want them to be domain independent. I want it not to run slowly if the same code could run quickly, because frankly, I love my laptop, and if it can fit on my laptop and it works on my laptop, I never want to see a supercomputer. I never want to go to the cloud for anything. I don't want it to run there and be done. The only way that's going to be happening if it really makes use of all available memory, all available CPU power. I want it to be efficient, even though I also want it to be in Python. Sounds crazy, right? I still want it. I want it to be scalable, because I don't want to reach the limits of my computer and just say, well, I guess that's it. Science stops. No more science. No, forget it. It's got to have this. It just has to, if you have more money, you should be able to get bigger. That's it. Your limit should be money. It shouldn't be anything about the software architecture. That's crazy. The way that generally can work is being cloud friendly. And that really means recognizing that data lies somewhere in the world, and it might not be on your machine. CPU and GPU resources lie somewhere in the world, and it might not be on your machine, and you need to be able to connect them up and really not have to worry about your software not supporting that. In the same vein, multi-architecture. If you're running Mac and your buddy's running Windows, you need to be able to collaborate. If you're running Windows locally and you need to work with cloud resources remotely, because those are usually running Linux, you should be able to do it. Otherwise, you're not going to be able to get your work done. And then these are a little less specific to Pangeo, but still things I personally find important. If a tool is only tied to a GUI, I will never use it. I love GUIs, but I will only want them for a minute, and I want them to go away, because I can't make that reproducible. I want it to be scriptable. I've got to be able to say, okay, I did it once, now run it 1,000 times. Run it for 1,000 times bigger problem. And so if it's not scriptable, I don't want it in my stack. Compositional, I don't want a monolithic thing that solves an entire thing from start to finish with one piece of software, because if it does that, it is of no interest to me, because tomorrow I'm going to want to do something different. This is research, it's science. We're pushing the envelope on things. If you're going to always do the same thing you always did, I don't even know what you're doing. Visualizable. I don't believe anything I can't actually look at with my eyeballs. And so if you have a whole bunch of components and some of them are black boxes, that's where your bugs are going to hide. No, you've got to reveal all the black boxes. So you need to make sure everything along the way is just easily dumpable on the screen, even for huge data sets that are remote. How do you do that? We'll use these tools. And it's got to be interactive, at least when it's not batch. When it's not batch, it should be as interactive as possible, because I don't want to have to write another script to test each different possible parameter when I could have an interface that allows me to really try everything out, because otherwise you're going to be repeating the same code you've always run. No, it's got to be shareable. You've got to have some way, if you're looking at it, you've got to be able to share your results with somebody. How can you do that? And it's got to be OSS, because I've got it working. I want it to work tomorrow, even though my license is expired. I want my buddy to use it, even though he doesn't have a license. I want to publish it so anyone can use it. They don't have licenses. No, it's got to be OSS. And so this stuff all applies to a set of tools that are generally considered data science tools. And you probably don't think of yourself as a data scientist, but I'm going to argue that data science is climate science minus the climate, beverage science minus the beverage, whatever science it is, minus the thing in front. It's whatever's shared across all these tools is about working with data, not about, and it's not like the domain doesn't matter, but there are a whole bunch of things that do correspond across fields. And those are the things that this stack focuses on. And so I want to split the domain specific from everything else, which we're going to do for everybody. So just to make things concrete, this is a plausible sketch at some part of Pangeo. Let's say you have data in ZAR. You can use intake to access a whole bunch of ZAR files and figure out what you want. You can read it into Xarray, work with it in memory with Xarray's API. If you want to write a little algorithm with it, you can write it with Numba. If you want to scale it up, you use Dask. If you want to render very large data, you might use Datashader to do that, or rasterize large data in order for subsequent computation. So Datashader is actually our project that crosses it's somewhere in between data processing and visualization, useful for both. And then there might be some domain specific code. Xarray Spatial is an example from our group that's is specific to raster processing, generally in a spatial context. And then you visualize. You can choose any visualization tool you want, but if you choose the ones on this list, they tend to have good support for distributed remote data sets. Like HVPlot will take your Dask-backed Xarray, render it using Datashader on a remote server, and show it on your local screen, even if that data was distributed across 1,000 different processors somewhere you've never even been. Doesn't matter, that rendering is done far away. The image of it goes to your screen and you can work with it. And then at the user interface level, typically people will do their first working with the data in Jupyter. They might share it using Panel or other dashboarding libraries, and they might do their whole organization or group with Jupyter Hub. So these are all things that are typical in Pangeo, I would say. And then what is SOSA? Well, SOSA is filling in other paths that are not based on multidimensional data. ZAR is based on multidimensional data sets, in-dimensional data, X, Y, time, whatever. Huge stacks or data cubes is often called. Parquet focuses on columnar data. DuckDB is a database format. If your data is more suited to a database like records and hierarchical bits of data. And then if you use one of these tools, particularly Kerchunk will let you deal with your domain-specific format and get it into something that's like ZAR or that effectively is ZAR. And then you either use pandas to work with it if it's data frame-like or columnar. Use Xarray if it's multidimensional. Use awkward if it is awkward, if it's ragged arrays like large collections of polygons. You use GraphBLOS if it's graph. Here, this is all dependent on what is the data structure fundamentally that you're trying to work with in your field. Is it time series? Is it image stacks? What is it? That's going to choose where you are here. And then you have to decide, are you on a GPU or not? And then you'll use one of these libraries. And then you can work with it using Dask, work with Numba, fill in. This is where you're going to have to do a whole bunch of work. which is whatever's for your specific field. And there are a lot of things in the climate science community that are now Dask aware, or that have examples showing how to use it with HVplot and so on. So a lot of climate science things already fill in this gray box. But the idea is that this box is not done by me or anybody I work with in Anaconda or anybody involved. It's done by the community, the people who know what they're doing for a particular domain. And then they don't duplicate all the stuff the other tools do. They focus on very specific things, using Numba to write their algorithms, Dask to distribute them, and so on. And then the visualization hands over after that. So you visualize using the same tools for everybody. And you can choose which underlying plotting library you want. They're all supported by HVplot, or you can use them directly, depends what you're trying to achieve, and then the same user interface. So that is SOSA. I'm arguing that SOSA, that you ought to architect your scientific approach in lots of different fields by focusing on this box and this box. Focus on this one to make sure your data is readable by Kerchunk or some other way, make it somehow fit into this. Something that FSpec can read, something that therefore is available to these libraries, and then focus on your data processing that's domain specific, which can be as simple as just writing a Numba file, a little bit of Numba code, a simple nested loop that sometimes that's enough. And then the rest is handled by all these general purpose libraries that everybody contributes to. Minor note, I just want to say we at Anaconda, it's a company. We have a lot of people whose salaries are paid. These little green squares here are put by projects that people have salaries paid by Anaconda to work on. So Anaconda does not make money. These are all open source. We're not making money off of any of these, but they come up in our work. We use them, we support them. This is something that we're heavily involved in. All of these are things that we pay people to work on their work time. So that's kind of why I'm the one giving this talk. I'm saying, hey, Anaconda is doing this. It's out there. It's already there. We've been doing it for 10 years. I've been doing it for longer than that outside of it. Other people have been doing it for longer than that. But it's something that we as a company are very committed to, this idea of just breaking through all the barriers of what Python can do. That's what Anaconda has been working on, but we haven't really told anybody. So that's what this talk is. So I don't have time to get down in the weeds on anything, but if you look at the slides, there are pointers to individual projects. There are pointers to, there's a description of what do you need to do. We've done everything else here, including many of the people on these calls have contributed to these projects, but the work is not done. You have to do things for your domain. Sometimes it's easy, sometimes it's really hard, but it's certainly easier than doing all the other work that all these other libraries do. And there's some examples you can see. And side note to point out, this is not the only stack that there is. If you want to use Ray instead of Dask, go for it. These tools won't support Ray. They don't currently. Maybe they could someday. They're not. So if you make that choice, you're going to have to find another stack. These don't support that with that way of doing distributed computing. They don't really support VEX very well. Polars, they're probably going to start adding Polar support as an alternative to using Dask and Pandas together. And they certainly don't support much in the way of what people have called big data before. That's all JVM-based, Java Virtual Machine-based, really very different from the sort of work that we're doing here. It's not, it's just not built around the fundamental numerical abstractions that these tools are using, other than a couple of things like Parquet and Arrow are really important members of this stack too. But then there are tons of other Apache tools. Most of them really, you put them in here, it's going to slow everything down. It's not going to be a good idea. All right, and then the rest, you can scroll through on this in your own time. It'll break down each of those things. And if you're not convinced why those are important, I try to convince you in those slides. So download that. And then the last bit is feedback. This is a talk that I submitted to SciPy, but then I wanted to go ahead and tell it to somebody. I didn't want to wait till July. So I gave it at my local Python meetup last week, and I got some good feedback there that I've already put into the slides. And so I'm hoping for feedback here. I'm really hoping for in anything that you know about, is there something like SOSA anywhere? Is there anything I ought to tell people about? Hey, in fact, this is better than SOSA. If there's something like that, I'd really like to know, because we kind of all dedicate our lives to this. And if we ought to change, please tell us. Probably this group is not going to tell me that, because you already bought in a lot of things. But certainly the second to last point here, if you have tools that you really feel like, why is that not on the SOSA slide? That's domain general. That's applicable to a lot of people. That's scalable, efficient, whatever. Please tell me that. So I'm really interested in feedback. This is the story that I'm trying to summarize and make sense of 10 years worth of work and lay out the next 10 years worth of work. So I'd really like to get the whole field of science on board with this. And if you have any feedback that would help that, please let me know. Thank you.
Awesome. Thanks so much, Jim. I mean, as you said, you're kind of preaching to the choir, but that was a great sermon. And this this choir member certainly appreciates it. And I have been singing the praises of this presentation and passing it all around to everybody I know in the community, because I think it's been very awkward in a lot of ways talking about the Pangeo stack, and this is just a better sort of paradigm, I think. And I love the way you presented the Pangeo stack with as a trace, or several traces through this more widely applicable stack. And I think you often say, you briefly said it, you said no dead ends. And sometimes I say to tell people it's future proof, which is sort of like the same idea that, no matter what where we go, this community will, with this stack will expand or move, and there's no, you don't paint yourself into a corner, no dead ends. And it's,
Oh, exactly. You can add new